This is the 24th video in our series on Lie algebras. And well, we're finally to the place where we're going to show that the classical Lie algebras are simple. And I think this is going to take 2 videos. We did SLn+1 in the previous video because that was like fairly straightforward, maybe the easiest of all of them. And today we're going to do SON. We'll do the odd case and the even case. So let's recall the outline here. So if we've got L, a classical Lie algebra, we're first going to find the Cartan subalgebra, which is the set of diagonal matrices in this case. And then we'll do the root space decomposition of L. And then, well, we're going to need the dimension of each of these eigenspaces L alpha to be 1. And well, if you are not remembering what all of these things are, I urge you to look at previous videos. We have a lot of terminology built up so far. And then the next thing that we'll do is show that for all roots alpha, this object right here is not 0. So notice inside we're bracketing x alpha with x minus alpha, and then we're bracketing that result with x alpha. And x alpha is the basis vector for L alpha. That's our general rule. And then next up, we'll find a set of simple roots, in other words, a base for the root system phi. We'll call those simple roots, or the set of the simple roots, delta. Next up, we'll take 2 simple roots alpha and beta. We'll find the SL2 triples related to those 2 roots. Recall that we can do that. We'll take H alpha and E beta from those respective SL2 triples and calculate this like wedge bilinear form beta alpha, which, if you recall, that's equal to beta applied to H alpha. The root beta, recall that that is an element of the dual space of H, making this a number. But then let's also recall that we can get that from doing the bracket of H alpha with E beta. That gives us this beta applied to H alpha times E beta, kind of by definition. Then we'll use all of this to build the so-called Dynkin diagram, which we talked about previously. And then that Dynkin diagram being connected implies that we have an irreducible root system, which in turn implies that we have a simple Lie algebra. So that's the sequence of events here. And now we're ready to look at SO2n+1. So let's maybe start by noticing that L has the following definition, but it really follows from the fact that it's the Lie algebra for a certain Lie group. But it has the following setup. It's going to be all matrices X in GL2n+1 entries in C. Those are going to be 2n+1 by 2n+1 matrices, and it satisfies the following rule. So X transpose times this matrix that's written like this. So it is a 1 up here, and that's the number 1. And then, well, we've got an n-dimensional row vector, 0 here, an n-dimensional row vector here, n-dimensional column vector, and n-dimensional column vector. And then we'll have a 0 here, a 0 matrix, the n-size identity matrix right there and there. Okay, so X transpose times that, plus this, so I'm just going to write that whole matrix again, times X must be equal to 0. So we can think about that as the definition for SO2n+1, although it follows from the fact that it's a Lie group for the Lie algebra for the Lie group SO2n+1. But this is about Lie algebras, so we can really think about it as the definition. But then that turns out to be equivalent to the following. So we've got L looks like this, or is made up of matrices that look like this. We'll have a 0 right here. We'll have C transpose here, B transpose here. We'll have B here, and we'll have C here. And I'd like to point out that B and C, in this case, are both n-dimensional vectors with complex entries. And then here we're going to have an M and a P. So those are matrices. Here we'll have a matrix called Q. And then because of this rule up here, this down here is forced to be minus M transpose. And I'll just write down here that we have M, P, Q are all in GLNC. So they're n by n matrices. Furthermore, we've got a rule satisfied. We know that P plus P transpose is equal to Q plus Q transpose, which is equal to 0. And then from this, we can observe that the diagonal matrices have the following form. The diagonal matrices, of course, forming the Cartan subalgebra by what we talked about before. So I'm going to write them first kind of in big matrix form, and then we're going to eventually use some maybe simpler notation where we take matrix with a 1 in exactly one entry, but we'll get to that. Okay, so we've got to have a 0 up here because of this rule, and then down the diagonal we'll have A1 down to AN, and then after that we'll have minus A1 down to minus AN. And then the off diagonals are 0, of course, because we've got a diagonal matrix. But observe that we can write that as follows. So that can be written as the sum as I goes from 1 to n of AI times the matrix EII. So that's going to be a matrix where you have a 1 in the II spot and a 0 everywhere else, and then minus En plus I, comma n plus I. So that's a matrix with a 1 in that n plus I spot and a 0 everywhere else. And now we can actually also use these rules right here to build a basis for L. And that's exactly what we're going to do now. And we're actually going to start the next board with that, with that on the board. Okay, so here's a basis for L. Well, not exactly a basis. We've got a basis for everything except for the H part. And then, well, arbitrary H is written like this, just like we discussed before. And I didn't point this out before, but we had a 2n plus 1 by 2n plus 1 matrix. And, well, we're going to order the rows from row 0 to row 2n. And the same thing for the columns. So we've got a 0, 0 spot. And that kind of explains why we have zeros right here. So I'll let you look at this, but notice that B and C, those are just forming vectors, just like we had before. There's like one index that is non-zero here. So we have BI as EI0 minus E0 n plus I. And then similar for C. And then notice MIJ has that definition over there, and PIJ and QJI have similar definitions. And now I'd like to start with a bit of an observation, which is really just a linear algebra fact. And that is, if we take ERS and we multiply it into EUV, what are we going to get? Well, this is a matrix where we have a 0 everywhere except for the RS spot where we have a 1. And this is a matrix where we have a 0 everywhere except for in the UV spot we have a 1. So by the rules of matrix multiplication, we know these inner indices have to be equal. And that gives us a delta SU. So that gives us a 1 if those are equal and a 0 otherwise. And then we have ERV. So that's, again, just from linear algebra. But from this, we can do some calculations. So let's notice that if we do H times BI, we get AI times EI0. And, well, like I said, that's pretty clear just from, well, exactly this matrix multiplication rule right here. And then similarly, if we do BI with H, we're gonna get AI, and then we'll have EI0 n plus I. But then from that, and the fact that the bracket of a matrix Lie algebra is simply the commutator, we have the bracket of H with BI, which, like I said, is HBI minus BIH, ends up being AI times, well, let's see, we'll have EI0 minus E0 n plus I. Okay, cool. But notice that that's exactly BI again. So we have this is equal to BI. But then we can make some similar calculations. But I guess maybe before we make those similar calculations, let's observe that that means that BI is an eigenvector for the add H operator, if you will. So we have add H of BI is simply a multiple of BI. Oh, this should be like our number AI times our vector BI over here. I forgot that. Okay, cool. So similarly, we have the bracket of H with CI looks like this. So it's going to be minus AI CI. We have the bracket of H with Mij looks like this. So it's going to be AI minus AJ times Mij. So as you can see, we built this basis right here so it would be a basis of eigenvectors for adjoint action from the Cartan subalgebra. Which really, I mean, that's exactly what we need here for this kind of decomposition. So that was kind of our motivation. And then we have the bracket of H with Pij is equal to, well, it's going to be AI plus AJ Pij. And then finally, the bracket of H with Qji is equal to what? Well, it's going to be minus AI plus AJ times Qji. Now, looking at all of these, that gives us a motivation for what the roots should be. And, well, I think that pretty quickly builds us or motivates us to define the following map, which will turn into the roots. So let's define epsilon I in H star by epsilon I applied to H, where H has that form up there, it has that form throughout the video, is equal to AI. But now, well, now let's observe that we can recode all of these in terms of the roots. So this one right here is exactly what? So it's going to be epsilon I evaluated at H times BI. And then, well, this is minus epsilon I evaluated at H times CI. And then, well, what's this one? So this is going to be epsilon I plus epsilon j evaluated at H times Pij, for instance. And then this one right here, well, that's going to be epsilon I minus epsilon j evaluated at H times Mij, which really tells us what our roots should be. I mean, this isn't completely from what we have because we left some out, but I think maybe the ones we left out are pretty clear, and we see that the roots are plus minus epsilon I, and then epsilon I minus epsilon j, and then finally plus minus epsilon I plus epsilon j. So those are our roots. And now, well, we see what the eigenvectors are just from this kind of calculation right here. That being said, let's recall those at the top of the next board and keep going. Okay, so here's a bit of a summary of what we just saw. If we had the following roots, these were the eigenvectors for those roots. So epsilon I had eigenvector bi, minus epsilon I, ci, and so on and so forth. And let's recall that in this case, we needed I not to be equal to j. And then in these two cases, we had I strictly less than j. But now let's observe that that immediately gives us a one-dimensional root space decomposition for all of these things over here, just kind of by visual inspection, if you will. And for instance, the root space of epsilon I is, well, spanned by bi. So we could write L epsilon I is CBI, and so on and so forth for all of the rest of them. Okay, so now, while looking at this, well, we would need to check this right here, this number 2, but maybe I'll leave that for you. That's just a matrix multiplication and, well, commutation exercise, really. But what you'll see is that you always get something non-zero. So in this case, for instance, if you have x alpha to be bi, then x minus alpha will be ci, just by how these things go. And then if x alpha is mij, then x minus alpha is mji. And then, well, if x alpha is pij, then x minus alpha will be qij. And then, well, like I said, you just have a bit of a calculation to do, but it's very elementary. Okay, so now at this point, we could go and look at the simple roots, or I shouldn't say look at the simple roots, see if we can come up with some sort of logical choice of simple roots. And it goes like this. We'll take alpha I to be epsilon I minus epsilon I plus 1. And this is going to be for I between 0 and n minus 1. And then we'll set alpha n to be equal to epsilon n. So we've got exactly n roots here. And now, well, let's quickly notice that we can get all of the roots out of this. So maybe I'll fit this in right here. So epsilon I minus epsilon j, if I is less than j, is simply, let's see, alpha I plus 1, ending at alpha j minus 1. So it's that root string, if you will. And then, well, epsilon I plus epsilon j, well, that's going to be something like this. It'll be alpha I added all the way up to alpha j minus 1. And then after that, we'll have twice alpha j added all the way up to alpha n. And then while looking at that, we see that we are able to gain all of the roots using our simple roots, meaning the set of simple roots is a base for our root system. Okay, cool. And now, well, we need to look at SL2 triples. So we need to do this calculation down here. So let's see, let's just write down here respective SL2 triples. So let's see, we could have E alpha I is equal to I plus 1. And then let's see, F, maybe I'll use alpha j here, is equal to mj plus 1j. And these are the SL2 triples with respect to the simple roots. And this is just based on, oh, well, let's look at this line right here. But notice that, well, we can put these two together in the case where I is equal to j and calculate h alpha I. And we'll see that that's going to be exactly equal to the bracket of E alpha I with F alpha I, which you can do the calculation and you'll see that that is EII minus EN plus I, N plus I. And then from that, we subtract EI plus 1, I plus 1, and then minus EN plus I plus 1, N plus I plus 1. Okay, so that ends up being our H alpha I. Okay, then now putting this all together, we're going to use the following. And, well, let's just keep in mind that these are kind of defining our SL2 triples. The indices aren't going to look the same for this calculation. So if we do the bracket of H alpha j with E alpha I, we should get what? So we're going to get this, let's see, wedge bilinear form, alpha I, alpha j, E alpha I. So that's kind of by the definition of this wedge, bilinear form, if you will. Okay, so that's actually enough to do all of our calculations and find the Dinkin diagram. So let's see what we get. Keeping in mind that this formula right here is a definition for this number. So you would simply need to do this bracket, see that you got some multiple of E alpha I, and that multiple that you got would end up being the definition of that object right there. Okay, so anyway, so what we'll have is that if you do the alpha I with alpha j, you'll get, let's see, 2 if I is equal to j. You'll get minus 1 if I and j are within 1 of each other. So in other words, absolute value of I minus j is equal to 1. And you'll get 0 otherwise. But this is not in all cases. This is in the cases when I and j are strictly less than n. So that means we also need to look at the case when one of them or both of them are equal to n. So also we'll have the following. So alpha n with itself is 2. Well, we know that this wedge thing of any root with itself is always 2. And then alpha n minus 1 combined with alpha n gives us negative 2, whereas alpha n with alpha n minus 1 gives us negative 1. And then all others, in other words, alpha I with alpha n, if I is smaller than minus 1, will give us 0. But from this, we can calculate the Dinkin diagram. And then Dinkin diagram has the following form. So here, this is associated to root alpha 1, root alpha 2. So there's just going to be an edge from alpha 1 to alpha 2. All the way down here, we'll have, let's say this is alpha n minus 2. And then this one right here is alpha n minus 1. And then this last one is alpha n. But since we've got minus 1 for all of these, we have a single edge. But since we've got minus 2 for one of them and minus 1 for the other one between alpha n minus 1 and alpha n, that gives us a double edge with the arrow pointing in this direction. So that gives us the Dinkin diagram for this SO2n plus 1. But notice it's connected, but since it's connected by this rule over here, that means our Lie algebra is simple. And now while we're at it, I'd like to point out that anytime you have a root system that gives you the following Dinkin diagram, there's a name for that type of root system. And that type of root system is said to be type Bn. That being said, type Bn is this thing where you have all single connections except for the last one, which is a double connection, pointed in that direction. Okay, so now let's do the case for SO, let's see, 2 times n. So in the case when we have SO2n, we've done actually a lot of the work already. And I'd like to point out here that we're looking at the case when n is bigger than or equal to 2. If n is equal to 1, then we have 2 by 2 matrices, and the restriction that we have on the 2 by 2 matrices means that you simply have a single matrix. And that single matrix is the matrix 1, negative 1. So you have a one-dimensional Lie algebra, which I guess we're not considering that to be simple or semi-simple for that matter. Okay, so let's see the setup. So if L is SO2n, then it's going to be 2n by 2n matrices satisfying this rule right here, pretty similar to the odd case rule. And then observe that we can build a standard form for the matrix like this. So we have MPQ minus M transpose. So that looks exactly the same or very close to being the same. It's actually the lower block of the 2n plus 1 case. And then, well, like I said over there, M, P, Q are all the same, and thus we can make an Mij, a Qji, and a Pij very, very similarly. And that brings this truncated version of the root eigenvector chart that we had in the previous case. And then our simple roots in this case will be alpha I being epsilon I minus epsilon I plus 1, as long as I is less than or equal to n minus 1, and alpha n is epsilon n minus 1 plus epsilon n. Okay, and now, well, you can find the SL2 triples exactly the same again and do this calculation. So what you'll end up with is the following. So we'll have alpha I, alpha j is equal to, well, it's going to be 2 if I is equal to j, that's not surprising, minus 1 if the absolute value of I minus j is equal to 1, and 0 otherwise. But this is only in the case when I and j are both less than or equal to n minus 1. And now the remaining case can be summed up as follows. So we have alpha n minus 1 with alpha n is equal to minus 1. Alpha n minus 2 with alpha n is also equal to minus 1. And then, well, and in this case, it kind of commutes. So alpha n with alpha n minus 1 is also minus 1, and alpha n minus 2 with alpha n is also minus 1. So that means we only have single edges. We don't have any double edges. And then while all of the other ones are 0. So if you do alpha n with alpha n minus 3 and so on and so forth, you will get 0. So that allows us to build the Dinkin diagram that looks like this. So it's got this nice little branch at the end. So this is the alpha n minus 2 node, this is the alpha n minus 1, and this is the alpha n node. Then I guess down here would be the alpha 1, alpha 2, alpha 3. So again, this thing is connected, well, in almost all cases. So let's note, if n is equal to 2 in this case, this turns into the following diagram, alpha 1, alpha 2, that has no connections. That's because we have no alpha 0, for instance, to connect to each of these. So, like I said, we don't have anything there. So it's not simple in this case. So the SO4, let's see, SO4, not simple. But all of the other ones are simple. So SO6, SO8, SO10, all of those will be simple, and that's because this diagram here is connected. And I guess I should say that any root system that has this diagram also is classified just as we had that BN classification, and it's classified as type DN. And now, I would be leaving something out. We talked about these types today. We had type BN and DN. Well, in the case when we have SLN plus 1, we had, let's see, n vertices, and they were all just in a chain like this. And we didn't talk about the type for that. That is in fact type AN. So we know about AN, BN, DN. So, I mean, it should stand to reason that next video we'll start with type CN, which will in fact be an SP Lie algebra. And then, well, after that, we have to look at the so-called exceptional Lie algebras, but we'll get to that. And that's a good place to stop.